Alright, this is video two of physics, and yes, I'm in the same clothes. Yes, I recorded this on the same day, and I hope you enjoy in the wake of the AP physics exam, or if you're coming from 10 years in the future, I still hope you enjoy. So, as the video title, we're going to be proving, I forgot to write it down, but x of t equals a cosine omega t for all x along the simple harmonic system where it oscillates back and forth. Now, you could guess on this problem, and that's actually a thing you can, it's like, there's like some fancy German word for it, it's called an Anch, something like that. You can actually guess what function would fit such a criteria just from looking at the motion. And yes, cosine fits it really well because you're oscillating, and that's how cosine or any trig, most of the sine and cosine behave. But you can 50-50 shot, you can get it. So, but we're not going to be relying on guessing. We're going to be relying on pure math, physics, all that stuff, right? We ain't going to be doing any guessing. So let's try and solve this right now. Okay, so one thing I want to note, one thing I want to say is this position is going to be distance from the resting point, which I'm going to name the resting point as over here since I named the amplitude as this much, right? One thing I'm also going to notice is that I'm going to set an initial condition just in case. I'm going to say that this starting point, so that means x of 0, has to equal the amplitude a, right? Because that's when we're gonna pull it all the way back to the amplitude and let it go from there like a slingshot, and it's gonna start oscillating back and forth. So now let's use some physics to set up some equations. One thing we do notice is energy is conserved. So let's write EI equals EF, and let's start counting up our energies from the start. From the start, it's going to be 1/2 Ka squared. And that's because all of the energy at that moment at the start is going to be potential, and none of it is going to be kinetic. Now, I said EF, but this is really just E arbitrary. It could be any number or any time, not number, time, when the energy is going to be there. And whenever it's any time, it's going to be its stress distance, which we already measured is x of t. We're going to just simplify into x. Its stress distance times its constant, and then it's squared, right? That's its potential energy plus its kinetic energy, which is going to be described as. Now, I would write velocity, but let's do some fancy calculus real quick and describe this as dx dt, which basically means the change in velocity over, not change in velocity, the change in position over time. So, look, we have x and dx dt in an equation. That is a differential equation. However, this is squared. I don't like that. We don't like squaring the derivative. If you want to square, that's fine. You can go and do your non-linear differential equation solutions and all that stuff and have fun with that. But I'd rather not. So first things first, before we do anything with that square, let's multiply everything by 2 and get rid of all of these annoying 1/2s. And then we cancel out everything. And let me write this down again. Alright, the next step I'm going to do over here, so I have more space and wiggle room. Let's do this. Let's move this kx to the other side and factor out the k. And then once we're done with that, let's divide both sides by m. Right, we're going to do 3 steps in one. So remember, we're factoring out the k, and we're going to get an a squared minus x squared because we subtracted it, right? Then we're going to divide by the m, and nothing's going to be on the side except for the dx dt squared. Right? Now, we can quickly take a cheeky little square root on both sides. and then we can separate these two. And you'll see why, so we can separate them and solve them without any confusion or anything. K over m, right? Times the square root of a squared minus x squared has to be equal to dx dt. Now you could put you should probably put a plus or minus actually, right? Because we're not taking any principal roots in here. It can be plus, it can be minus, we don't know yet. But you'll see that it would not matter, and I'll explain why. But let's get to that part first. Let's multiply dt on that side because there's no x's nor t's, so the default should be dt. And then divide this square root of a squared minus x squared on this side with the dx. We're separating our variables now. So let's do that. Okay, now integrating this could be tricky if you don't know trig sum, but you guys have watched my videos, right? Yes. So now we're gonna start. Now we're gonna integrate it. Sorry for the integration sign. It's really hard to write this way, but let's do this. So remember, we're talking about trig sum, right? Let's use cosine because sine won't give us any problems when you square root it. So let's do that. Let's let x equal to a cosine of a new variable, let's say theta. Dx equals negative a sine theta, d theta. Both of them deserve their d thetas. So let's substitute now. Let me just write this like this vertically. This is gonna be dx over the square root of a squared. Let's factor that out because we're squaring both of them. 1 minus sine squared theta. And we're not using dx, right? We're using d theta now. And d theta is going to be negative a sine of theta. Oh, it's not a sine squared, it's a cosine squared. My bad, but yeah. So this under radical 2 is sine theta. That is your trig identity plus a square root. Same here, square root of a squared is just a. So now we can cancel out a bunch of things. In fact, we can cancel out this, and all the left it is with negative d theta, and we're integrating that. Forgot the integral sign. And that's just going to be negative theta. And remember, we're doing trig sum. We're doing trig sum, right? We need to go back. So let's just say. So now we don't actually. This doesn't deserve the d theta. That's a brain fart on my behalf. I'm so sorry. We need to go back to x word. So we're gonna substitute. We're gonna isolate theta. Isolate theta, and we're gonna get theta is gonna be the inverse cosine of x over a. So this is actually going to be the negative inverse cosine of x over a. We're not going to worry about a plus c right now because we're solving differential equations. I'll tell you why. So when you integrate this, one thing you should notice right now is that the square root of k over m, in fact, is your omega, your angular speed. So to save me some writing space and save you some time, let me just substitute that and call that omega. So omega t, right, plus minus is going to be equal to, actually no, it's a plus c equals negative cosine inverse of x over a. Capital A. Now, the reason why I didn't take a plus c on this side is because you can technically subtract that c on both sides and you can get like a new c. But a new c is just another c, so just name it another c. So that's why I'm just skipping that step instead of subtracting that c on two sides. So we're left with this. Now let's rewrite this over here so we have more space. Okay, so let's isolate x because we're trying to find x at t. And now you can see it, but this should be something that is bothering you slightly. So yeah, well, I'll explain it though. So let's try and solve this first. Negative on both sides, this becomes plus minus. Now minus plus. We're doing plus minus, so not because minus plus because negative omega t. Now that plus in this case, that plus minus can go to that c. That plus minus is gonna go to that c, but that's c1, so let's name this c2 because that's a new c. Cosine inverse x over a. Take the cosine on both sides so that inverse cancels out and then multiply a on both sides. So let's do a cosine of omega t plus c2 equals x of t. We ain't done yet. We're trying to find x of 0 equals a. So this becomes x of 0, which means this becomes 0. This would have to be 0 too, because we're going to have cosine of 0, which is 1. A equals a. So since this needs to be 1, this needs to be 0. And since this is already 0, this is also 0. So this in fact is 0. So our final equation, let's write this like this. Switch the sides so it looks more pretty. A cosine omega t. And that's your proof for this. Yep, hope you enjoyed.